Let's take a look at the logic of ordinary least squares, or OLS regression. What's the goal? The goal is to find basically a straight line that fits the data best, in the sense of minimizing the total vertical distance between the line and the data points. Let's take a look. So here's an illustration. We've got a scatter of points, which represent basically elements in a data set, where there are two variables, x and y. X and y could be many things. So let's consider a possibility that maybe x is something like the daily food intake of a cat, and variable y is the weight of the cat, measured in something like pounds or kilograms. Then each point in the data, for example that one, represents a particular cat with its daily food intake and its weight. So we'd like to fit a line that goes through that scatter plot that will capture the relationship between how much the cats eat and how much they weigh. Now we're going to think about this in a particular way, which is we want to ask what line would provide the best prediction of y given a particular value of x. So if we knew the food intake of a particular cat, but we didn't know its weight, we'd like to be able to predict its weight given its daily food intake. Now to get that, we'd want a line that would pass in some sense through the vertical middle of the scatter plot. Let's see what I mean by that. So here's our scatter plot again. Let's consider the cats that don't eat very much. So we could take sort of a slice of the data, if you like, and let's just look at the cats between these two vertical lines. So this one, this one, this one, and this one. Now if you look at the average among those and ask the question, what does it weigh? It's somewhere around here. That looks like about the average weight of those cats. If we took a slice of cats that were piggier eaters, so for example this range of cats up here, we can see, not surprisingly, that those cats seem to weigh about on average that much, so they're heavier cats. We'd like to find a line that would allow us to predict for any given cat with a particular eating habit how much it would weigh. And so that would be a line that would go somewhat through the middle of this slice of the data, the middle of the middle slice of the data, and somewhere through the middle of the high slice of data. And you can see that that line is going to look something like this. And that's what I mean by the idea that it slices through the vertical middle of the data set. It offers us a prediction of the cat's weight based on its eating habits. Now, let me redraw that sketched line that I think goes more or less through the vertical middle of the data. And let's ask, what's the formula for that line? Well, you remember from somewhere in middle or high school that the formula for a straight line has an intercept, which in this course, for now, we're going to call B0. That's where it passes the x equals 0 axis. And it has a slope, and the slope is the rise over the run. And the rise is the change in y for a unit change in x. And we're going to call that slope B1. So our formula for the line then is going to be that y for any given cat can be predicted by B0, the intercept, plus the slope times the food intake of the cat. So for cat I, we predict that its weight is that formula of its food intake xi. Now, to identify the fact that we're not talking about the actual cat, but the prediction for a cat, we put a little hat over the y. So yi hat here represents the predicted weight of the cat given its food intake xi and the formula for our line. Now, once we have that guesstimate of the line, which I will draw again right here, with its intercept and its slope, we can see that the line is not a perfect predictor. Unless all the dots lined up perfectly on a straight line, we would never have an exact prediction. And we can see that for cat I, our prediction is not actually accurate. So there's cat I's actual values of its weight, y, and its food intake daily, x. Now, what does our line predict that its weight will be? Well, given its x value, the line right there predicts that yi hat should be somewhere about there. And this distance that separates the actual value from the predicted value is essentially the mistake that we've made with our straight line prediction. So this we can think of as the error or the mistake, that vertical distance, the deviation between the actual value yi and the prediction of the line yi hat. So let's look at what that formula for that little mistake or error would be. So the error is going to be given by this formula, and we can see that it's the gap between the vertical gap between the actual value yi and the predicted value yi hat, but the predicted value yi hat is given by the formula for the line with our values of the intercept b0 and the slope b1. So we substitute that in there for yi hat, and then we allow the negative to be distributed, and we end up with this little value here, that the value of the error or mistake for that observation is yi minus b0 minus b1 times xi. So you can see that in the case of observation I, referring back to our graph, this deviation is positive. The actual value of y exceeds the prediction. But for other values, it would be negative. And let's take a look at that. So here was our cat I, but here's cat J. Give it some ears and whiskers as well. Now cat J is below the prediction line, or the regression line, right? So for cat J, its value of x, or its food intake, is down there. Its value of its weight, the weight of this cat, is there at yj, and we can see that the predicted value is way up here on the line. So the line overpredicts, and therefore the gap between these two, between yj and yj hat as predicted by the line, is actually negative. So the error here is, or the mistake is negative. If we were to add up all the mistakes, the positive mistakes like I and the negative mistakes like J, the positives and negatives would tend to cancel each other out, and in fact, they might cancel each other out entirely and add up to 0. So to prevent that happening, ordinary least squares squares all the errors. And that makes everything positive, and then we can add them up and try to minimize them. So we get to the punchline at this point. Our goal is to choose the intercept b0 and the slope b1 for that line that minimizes the sum of squared errors or squared mistakes. And again, here's the mistake for each observation I. We square it, and then we add it up. And remember the summation notation. The sum from I equals 1 to n. N is the number of observations in our data set, the number of data points. In this case, I think it was 11. Substituting in for yi minus yi hat, we had that little expression, and this finally is the sum of squared errors, or the sum of squared mistakes, vertical mistakes, in our scatter plot given our proposed line. Now, if we could find the values of the intercept and the slope, b0 and b1, that made that as small as possible, given our data, given the scatter plot, we would have the best fitting line according to the ordinary least squares estimation, and we would call those the OLS estimates of the intercept and slope. And just to reiterate, note again what's the special property of these OLS coefficients, the intercept and the slope, b0 and b1. They give us the straight line that makes the best overall prediction of y, that is, of the weight of the cat, given or conditional on the x value, in this case the food intake of the cat. So if we know a particular cat's food consumption habits, the OLS line is the best straight line that will give us a prediction of that cat's weight, given what we know. And that's the key to ordinary least squares, and we'll pursue the formulas in another segment.